Assalamu alaikum warahmatullahi ta'ala wa barakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, let's continue our tutorials about computational fluid dynamics CFD. In this video, we're gonna complete our project about radial turbines. In this video, we're gonna use CFX to carry out the simulation with the volute and without the volute. Okay, so let's get started. Here we have here the radial turbines. This is not my presentation. This session delivered by this professor. It's available online. And here is the just an introduction to the basics of the radial turbines. And here the volute. Then you have to find the nozzle vanes, and then the turbine itself. Okay, and here is the turbines and the applications of it. You can use these presentations. And here we have the basics of thermodynamics and the efficiency of these turbo machines. Here we have the nozzle efficiency, the compressor, and the turbines, and the HS diagrams. And we have to know if you work with ideal gas or real gas. So here is the turbine as entropic efficiency against the pressure ratio for various polytropic efficiencies, and here is the gamma is constant. Okay. Here the compression. You know that the isentropic efficiency of the turbine, yes, is delta H actual divided by H. Here is the H1 minus H2, this H2 actual, divided by H1, the enthalpy at the turbine inlet, divided by the isentropic efficiency at the turbine exit. And so this delta H is lower than H1 minus H2S. So to get the isentropic efficiency, you have to get the enthalpies difference. So now let's start. We have here, we're gonna carry out the simulation without the volute at first, and then we're gonna complete the tutorial with the volute. Before you open CFX, you have to here the mesh dependence study. It's according to your model and the accuracy you need. Yes. So here is a research of design performance of a multi-stage supersonic turbine, and you have to know the recommended Y plus for the mesh to capture the supersonic phenomena. Okay, and because you have to get the required Y plus, and then you can carry out many mesh sizes. Okay, and then you can transfer the mesh into CFX. So you have here 3 mesh sizes. Let's take a look on this. Down here, the boundary conditions for subsonic outflow, the circumferential and radial flow angles, total pressure, and total temperature are extrapolated from the interior of the computational domain, and total to static pressure ratio is specified at mid-span of the computational exit, and the pressure at all other radial locations at the exit is obtained by integrating the equation by radial equilibrium. So it's according to the method you follow, and it's really complicated situations that you have to be involved with. The simulations here, and for the y plus, the average value of y plus, the non-dimensional distance of the first grid line above the surface was approximately 1. So here is the point. Here is the point to get a high quality resolution. You have to check out the y plus recommendations for the last from the references and the papers, and you have to follow. I have here. You have now, you know that y plus is around 1 or lower than 1. So in this, here we have a thesis. You will find the equation of the y plus to calculate delta. Here is the model, and the element size at the wall in the wall normal direction is calculated by these formulas. You have to, y plus is 1, and here's the kinematic viscosity, and rho and times the u. Okay, so you have to get this value and apply it here. So I have to apply this value. Here is the wall. We need to specify this distance. This is what I mean. This is the importance of y plus. Okay, and here is the mesh, and here you have to specify or try many scenarios of this mesh. Like this. You find the mesh, no problem in it. Okay, after finishing this, you have also to run many mesh sizes for the rotor. So the mesh dependence study is very important, and after specifying y plus according to the study, you have to find out the wall distance, and then apply many mesh sizes, then run many simulations, and you can stop if the solution does not change anymore. And here is the mesh of the rotor. Also, you have to change these parameters to specify the first wall thickness or distance. This distance, the first layer. Okay, after finishing this, okay, now our CFX. Notice that I have here 3 standard mesh sizes. I decreased the wall distance to a limit that this tether mesh is very low in the size. Okay, the wall distance is very low, and this causes instability of the simulation. So you have to know what is the optimum mesh size. It is not good to decrease it. No. Here the roller. So let's open CFX setup. I found that the values that are based on this very small size mesh are not good at all. The ranges are very high, so I selected the other mesh. So you have to do this. And here you may use the gases, or you can add materials. So you can insert here material like this. This is also a thesis, and they used a perfect gas, a real gas. Real gas, you have to calculate the properties. Here they used ideal gas and real gas, and the percentage of the error between the two simulations. Okay. And here the setup of the ideal gas, and then the real gas. It is based on these models, and here the calculations that you can carry out to know the settings or the properties of your gas. So let's insert material, real gas. Now here you have pure substance or fixed composition mixture, variable, homogeneous binary mixture, reacting mixture, or hydrocarbon fuel. And pure substance, the material description on thermodynamic state is going to be gas. And here the general material or table, or this option. And here value or ideal gas or real gas. So here the model that you have to select, and here the molar mass, and the other inputs that you have to calculate or to get it from the company, and the specific heat capacity. You have to fill all these, and after finishing the table generation, you have to set the minimum temperature, the maximum temperature, and the transport is very important, the dynamic viscosity according to kinetic theory, or this, and here the rigid non-interacting sphere, and thermal conductivity also, and it is modified Yukin. After this you can click OK, and that's all. What we know, are not gonna use this gases. So after finishing the material, click on tools. But before this, you have to check out the geometry, please. You have to know if this assembly is the required assembly or not. Here you can see that there are some millimeters. Here the interfaces are not tangent. So please, I recommend to handle the geometry before entering the CFX. But if you got this problem, notice you can use transform mesh and translate this mesh by delta. You can choose the distance you need. Okay, you can like that. Notice that you can change the position of the mesh like that. And also for the stator and the rotor, like that. Okay, but I'm not gonna make this. Okay, let's make it. Okay, let's close it. Please be careful. It's recommended to handle the geometry before the CFX. So okay, if it's okay, so open the turbo mode. Here the radial turbine, and it's gonna be steady state. Notice this arrow. This is the direction of the rotation. But our turbine, we're gonna complete this. Here is positive 3600, but I need it to be clockwise. So minus. Okay. And we have to select. Notice you have to make it minus to make it clockwise. And here is the rotor. So I'm gonna use this passage and then add components. It's gonna be a stationary passage 2. Then next, we're gonna use air ideal gas. If you have a material like any other material, you have to find it here. Okay, you can add the material like the real gas, and you will select it from here. And here reference pressure, I think it's 1 atmosphere, and if you wanna have total energy, okay, and shear stress transport is recommended for this kind of simulations, and according to the thesis that I have. And here you have 4 options, none, and it's not recommended to make this. And you have to P total inlet, P static outlet, P total inlet, mass flow outlet, mass flow inlet, and P static outlet. I think that it's more accurate to get this option, but you have to know that you only have to enter 3 values here. This is the total pressure at the inlet. This is the inlet, and here the total T in Kelvin and flow direction. You can make normal to boundary or cylindrical components or Cartesian. And here the P static. So the interface here, stage represents the mixing plane, and here the frozen rotor. Here in the stage model, also called mixing plane model, the rotor frame is rotating. Unlike the frozen rotor model, the flow priority fluxes are circumferentially averaged upstream of the interface to obtain the boundary conditions for the downstream component. So this is the mixing plane interface. As an effect of the circumferential averaging, all transient behavior of the flow is averaged out, and the only boundary conditions for the downstream interface are steady. This results in higher accuracy for flows with small circumferential variations. So the stage model is more computationally demanding compared to the frozen rotor model, so you have to know these basics. And transient rotor steer model, the true transient interaction between the components is resolved for maximum accuracy for the SPP model or the FT model. This is the same method as the frozen rotor model, but the relative rotation is also taken into account. Okay, so this model can be used for the same interfaces as used in the frozen rotor and stage models. So we're gonna make it here stage and then next. Yes, and here the interfaces. You have to select the interfaces. The interfaces are the outflow. This is the outflow and the inflow passage. And the outflow, where is the outflow passage? This. Oh, I'm sorry, this is the inflow passage. Yes. Stage. Next. And here are the inlet and the outlet. Finish. Okay, that's it. And here is the steady state. And that's all. No other. Here the software control is very important. High resolution, and please to recommend it to be more than 500. It's gonna be 1,000, and you have to see the conversions and in the monitor of the monitor. And here RMS, increase this accuracy as an initial guess. And here the output control results and the backup. You can carry out backup results. And here's the monitor. You can find the efficiency output compression. You can choose this or both, and total to total or total to static. It's up to you. If you use real gas material, I think that you have to find the efficiency output and check on it. And that's it. So this is the steady simulation. Click close. And here is the solution. Here you have to check on the double precision, and here is the parallel. It's according to your PC, but I'm gonna use serial because I have I need the parallel processing for another thing. Here you'll find the convergence, the momentum and mass, the transfer turbulence, and the wall and boundary scale. You can right click on the monitor priorities here. Okay. And here you can save this picture or export plot data to an Excel file. Okay, and you will find the conversions here. So now we're gonna stop the simulation and complete the other part. Okay, but before finishing it, here you will find the efficiency monitor, and you can right click on the monitor priorities, and here is what I wanna show you. You can check or uncheck the things you don't wanna see, and you can make the flow at the inlet or the outlet. You can click on the PMAS here to see the flow. You will find the mass flow rate here fluctuating. Okay, you can uncheck this and click like this. You will find this. I think the negative value is according to the direction of rotation or something like that. So here are the mass, and also you can simulate the force, normal or tangential force at the blade, like that. Also you can see the moment, the tangential moment acting on one blade. These values are for one passage, I think, and one blade. So this is the torque of one blade and tangential force with the moment. And this is very useful to get this, and you can use it for later calculations. Okay, and the other things, and the time step accumulated or the current time step, it's no problem. Okay, let's close this. And here are the settings for the steady state. This, if you don't want to complete the solution as transient. So now what if we have to carry out steady state and then transient model? So open the setup. But please, if you take the decision that you will carry out the steady state and then transient, you have to reset the settings from the beginning, and please repeat what I did here. Okay, and then we're gonna make more step. Duplicate this and rename it as transient. Okay, this is the transient, and here the steady. I'm not gonna touch this. Here's the transient. The analysis type is gonna be transient or transient blade draw. So what's the difference? Gentlemen, if you have rotor and stator, and the rotor, the number of the blades of the rotor is not the same as the number of the blades of the stator. We have 15 blades here, for example, and here 17 blades, and so the pitch angle is not equal. So if the number of blades or the pitch angles are the same, use transient. If you have different number of blades, you have to carry out this. The transient blade draw modeling can be computationally expensive to predict the unsteady phenomena that occur as a result of the interaction between adjacent blade rows, blade flatter, or boundary disturbances. it can be even more expensive if you need to include more than a few passages per blade row to capture the phenomenon more accurately. So, in typical turbomachinery applications, it's very common that one or both blade rows have a prime number of blades per wheel. Formerly, in such cases, it was necessary to model the whole 360 wheel in order to attain the required level of accuracy. So the transient blade row models available in Ansys CFX make it possible to reduce the size of the computational problem, memory and computational time, by solving the blade row solution for one or two passages per row while still obtaining reasonably accurate solutions, therefore providing a solution to an equal pitch problem. And here's the problem, or the point, between the blade passages of neighboring rows. So we have here transient blade row models available in Ansys CFX: profile transformation, time transformation, and Fourier transformation. So the profile transformation method, overcomes the unequal pitch problem by scaling the flow profile across the blade row interfaces. In the time transformation method, the unequal pitch problem is overcome by applying a time transformation to the flow equations that enable the use of simple periodic boundary conditions on the pitch-wise boundaries. In the Fourier transformation method, a phase-shifted boundary condition with Fourier data compression is used to account for the unequal pitch between the blade rows passages. So the Fourier transformation and time transformation methods can be used to apply periodic conditions that are phase-shifted in time in order to account for the unequal pitches between adjacent blade rows for transient rotor stator cases, or to account for inequality between signal and domain pitches for boundary disturbances cases, or to account for the inter-blade phase angle for blade flutter cases. So now you have to get a lot of information about these simulations. And here, first of all, you have to check out the interfaces. You have to make this transient rotor stator, and here the solver control high resolution, and here the maximum coefficient noise is recommended to be 50 as an initial guess to enhance the resolution or the convergence, as I know. And here the output. Sorry, first we have to click on this and click on time transformation 1, and in between rotor and stator, this one to R1, and here you have to check out all these inputs, and here the time steps per period. Gentlemen, if you set this 100, you will not be able to stop the simulation before finishing these 100 time steps per period. So if you have 80, if you set this 100 and you stop the simulation before finishing them, you will not be able to use the CFD post. You have to read the simulation from the beginning. And here are the periods per run. Please, you have to read about all these settings to know what's going on. One more thing, you have to make initialization for the transient. You can make it automatic or to set your values according to the your experience. And please, the turbulence is very important to know the turbulence intensity. If you set the turbulence intensity that is not true or accurate, you have to carry out many simulations and to know what is the reasonable turbulence intensity, because it is very important to know this value. It will affect your simulation. Okay. And for S1 initialization domain. This is just a tutorial, so you have to check out all this. You can make automatic with value, and you have to enter this value. Then okay, so now we do not have any problem. For the last thing is the at least you have to make configurations. Insert configuration. It's gonna be for the steady one. Start simulation and steady, and okay, and transient. This transient is gonna be transient and end of configuration, and you will start the configuration by the steady, and then this will start. Run definition, okay, and here are the initial values. It's gonna be the configuration results. So after finishing the steady state solution, after being converged, the transient solution will start after it automatically. So if you wanna carry out steady state and then transient, you have to make this from the beginning, okay? Like what I did in centrifugal pumps tutorial. But in centrifugal pumps, I used transient, not transient blade roll. Then click close and run the simulation without any problems, and the conversions of the time transformation, I think it's gonna be like that, fluctuating, and like this. This is the convergence of the time transformations, fluctuations. You can see here Ansys CFX modeling tutorial. It is available on YouTube for Fourier transformation and time transformation. So this is the modeling fluid flow and vent volute using FT TRS. You can watch it on YouTube, and the other this multi-stage time transform. It's available on YouTube, and you will find these settings. Okay, this is the part number 1 of this tutorial. Now we're gonna talk about the CFX with volute. I have the geometry of my friend, and we're gonna use it to carry out the simulation, steady state, and then transient blade roll with the volute and nozzle and the rotor. But I'm sorry, before start this stage, for the time transformation, there's a very important thing you have to do before starting the solution. So you have to define the parameters you need to check out after the solution in the CFD post. You have to make this, or you will find nothing. Here, notice okay, analysis transient blade roll. The essential option has been selected. Essential only provides a limited set of variables. So it's open output control, and here the backup. You can make the backup and time. And here the essential. No, we're gonna make selected variables. And here you can select the parameters you need to check after the solution is CFD post, Mach number, and maybe the isentropic total enthalpy. You know, you can make this to check out the efficiency or the isentropic efficiency without the monitor, and the pressure, temperature, static enthalpy. Please, you have to select everything you need, because if you do not do this, you will not find it. Okay, you will find these parameters in the CFD post. And here is the monitor. Gentlemen, you can carry out this monitor, or here is the isentropic total enthalpy. Why? You know that the turbine efficiency, if you do not have the, you want to now calculate the turbine efficiency, this isentropic efficiency H1 minus H2 and H1 minus H2S. So you can make a monitor at the exit of the rotor to get the value of the total H2S, and make a monitor at the inlet of the rotor to calculate the total enthalpy, not total isentropic enthalpy, and also make a monitor at the exit to calculate the total enthalpy. So you have total enthalpy at the inlet and the exit, and total isentropic enthalpy. So you can get delta H and divide them, divide this by this to get the isentropic efficiency. This is the case of the accuracy of you if you do not find the efficiency output monitor. And here you can select like that at the outlet, and please, for accuracy, you can set the coordinates, but just another monitor. And here is the total enthalpy, not isentropic enthalpy. Okay, so, and another point here, the enthalpy, total enthalpy at the outlet. So we have two monitors for the enthalpy, one isentropic and the other is not isentropic, and okay, and so on. Then you will find your monitors during the solution, the simulation or the conversions. Okay, so this is a method for the efficiency. We're going to talk about the expressions the next couple of minutes. So here the geometry XY, let's make it millimeters. File, import external geometry. It's going to be step file, a step file, final volute. It's going to be add frozen, please. I think it's important. If you use Fluent, if the volute is add material, the rotor has to be add frozen. And if the volute is add frozen, the other part has to be add material due to using the sliding mesh technique. So we're going to use this add frozen, not add material. For the sliding interfaces, here is the flow of the volute. It's better to use this, not what I did. But anyway, you can transfer this to this. And here open the mesh. And here the mesh, first of all, this is not a mechanical simulation, it's CFD simulation using CFX. And here the sizing, make it fine, smoothing the high, and make it here 180. And minimum size is going to be 1 millimeter. It's 1 millimeter. Decreasing the size will enhance the mesh. Okay, here's structured mesh, and here are the statistics. Skewness, the minimum skewness, and here the maximum skewness 0.93. It's recommended to not be more than 0.98, so it's okay. Here, so I think that this mesh is very good. Here the skewness. You can use or minimize the size. Is according also to the mesh dependence study. This is 1 millimeter. It's a random size for this tutorial only, and you can use any other techniques to decrease the size. Now we're gonna click on this side and this side and create name selection. Here's the volute, outlet, and here's the volute inlet. This is the volute inlet, and here the flow, the volute outlet, this and this. You have to be sure that you selected the two faces or the face. Okay, click close, and then get me the rotor mesh. And stator mesh. And the volute. You have to update this. Okay, after being updated, open the setting. Here for the volute assembly, we're gonna use profile transformation because it's easier than the other methods. Okay, gentlemen, also if you wanna insert materials, up to you. Okay, also have to check out the assembly, and if you have a problem with the this, you can make translation. You can make translation for the stator or the rotor to make the good assembly, but because you may make inaccurate assembly, it's recommended to make this before the CFX, or you can use transform mesh like what I did. Here's the translation. You can move this in any direction, but if you make the distance very high, the tutorial or the CFX will not be able to find the solution, because you will find the mesh, this mesh and this mesh and this mesh are not connected well. Okay, so okay, open thermo mode and radial turbine, steady state, and the components. Passage 1. Stator 1. Stationary 1. Stationary 2. Select B14 or any B. Do not select any other things. Next, I'm gonna use air, gas, shear stress. Here we can use P total inlet. And here. And here the trick, the mass flow, please, if the whole machine has mass flow rate 1 kilogram per second, so it's per machine, and do not enter per passenger component. It's going to be calculated automatically. Stage or frozen rotors according to, and here the sliding mesh, or I'm sorry, the sliding interfaces. It's going to be the outflow, and here's the inflow passage. Yes, the passage inflow. Okay, here are the interfaces between the stator 1 and rotor. Okay, this and this. So you have to add interface between S1 to S2. So S1 is the inflow, not the outflow, this part, and the second is going to be the volute outlet. That's why I used this name selection. It's going to be also stage, because steady state. And here we have only the R outlet, the mass flow rate. So you have to add boundary in stator 2, stationary 2, inlet. Then it's going to be the volute inlet. And the volute inlet is going to be the total static pressure and total pressure. You have to set the same boundary conditions. Okay. Okay. Can close it. It's not normal to get this message. So it's okay now. Here is the steady. Okay. The solver control also we have to make it high resolution, and here 1000, and increase the accuracy for MS. And here the output control, backup, and monitor. Here the efficiency, product to static. Now we have to duplicate this for the transient blade row. Here is the transient blade row. Okay, let's initialize the solution for the simulation. Medium intensity, please. You have to know or measure the intensity at the laboratory, or you can make the guesses that are reasonable for your simulation. The intensity affects your solution. So you have to change the boundary conditions and make matrix to get the required solution. The intensity may be differ from the inlet to the rotor to the stator, the second stator. It's very complex. It's not easy to get the required results from one kick. This tutorial is just to show you the setting procedure, not to follow it to get your results. So here the trick in the interfaces have to be transient rotor stator. If you make it stage as it, you will not be able to run the simulation automatically. Transient rotor stator, and then here transient grid row. We are gonna use profile transformation, and here time steps. It's okay to stop this simulation before reaching 100. It's not like the time transformation. Please, you have to read about the number of periods per run and everything, okay? So now we have to carry out the configurations. So the configurations, steady, and nothing more. And insert configuration transient end of configuration of steady, and run definition and initial values, configuration results steady. It's okay. Now we do not have any problem, and you can just close this and run the simulation. But now we're going to talk about the expressions and the monitors. Gentlemen, you can, here for the steady state, you can make monitors, additional monitors. This monitor you can name it, and you wanna make a monitor to check out the specific CP, the specific heat capacity at constant pressure, CP or CV. If you use a gas that its CP is not constant, so you can monitor the heat capacity at the point you need. Okay, I'm gonna select a random point. for this tutorial, and then apply. And also can add monitor number 2. It's preferable to name the monitor with the name of the parameter. This you have to select all you need from here for the monitor, especially for the transient behavior, Mach number, and for the efficiency you can monitor the enthalpy, the total enthalpy at the exit, and the asymptotic enthalpy at the exit, and the total enthalpy at the inlet. Okay. Okay, and so on. Then you will be able to find the values of the enthalpies, and then you will find the total at inlet and total at outlet, and the asymptotic efficiency at the outlet. So another thing to use here, also we have to do the same monitors at the transient. We did it in the steady, but we did not do it in the transient, so we have to repeat what I did in the steady to have monitors in the steady and the transient. Now, if you have to write an expression, for example, there is an expression here for the efficiency. The correct way to calculate turbine efficiency is rotor torque cross the RPM divided by m dot time delta HS. So this is torque times omega, or the torque times the RPM. So this is the efficiency, and like this. It is not based on delta H, H1, not H2. No, it is according to the power of the turbine, torque times the RPM divided by delta HS. So you can get H1 and H2S by the monitors, and so this is the, I think this is the idea. And get the torque also from the monitor, but per blade, and the enthalpy. Third expression, torque, and the torque is right click, and here are the functions, CL functions. You'll find, sorry, and here is the torque around Z at the mesh locator 2D is the blade. Please, you have to know this is the blade apply. Okay, here is the torque at the blade, but which blade? To be more accurate, you have to know that you have R1 blade and S1 blade, and that's it. So please be careful when you use these expressions. You have to make the accurate locations. I did not use the expressions and found accurate results. So please be careful when you use these expressions, especially the and here you can make omega. Okay, no problem. For the rotating speed, suppose that it's 1000 radian per second. So click apply. Now you can see the expression of the power. The power is like that, torque multiplied by the rotating speed. But please, I'm not sure of this because I did not use it before. And here the omega. The problem is with the units. So please, if you use this, I got this also this expression from the CFD forum. If you use it in mass flow average, you can find all of these. You can make this functions together based. You will find mass flow average, mass flow average absolute. Anything you need, you will find it here. Yeah, at inlet, like this. Right click the mesh locator to the. You will find there is the outflow and inflow. Okay, and volute inlet. Yes, this is the volute inlet. Just to show you how to write an expression, but I'm not telling you that this is the right thing to calculate the efficiency. No, it's not. I do not say this. So this is the. We can make this. So this is the power expressions torque times the rotating speed. So now we have this. The torque will be calculated automatically from this expression. The torque at the blade but the torque at the blade, I think that you have to multiply it by the number of the blades. So you want to now monitor this power. How to do this? For the steady, go to the monitors and add monitor. No, not like this. Yeah, I think you have to add monitor. Yeah, expression. And that's it, right click the expression, and here's the power. Okay. Also for the transient, I repeat, I'm not sure of this expression. I'm doing this just to show you how to use the expression method in calculating anything you need. Okay, and here. So now also we have here the CFX expressions. Please, you have to take a look on this expression and to know the commands and how to use the expressions to get the parameters you cannot get. Now we have finished this, and I have just to close the CFX. And then if you open the CFD post after running the solution and after finishing the solution, the results of the enthalpy, you will find it at the blade. Okay, it may be 1 kilojoule per kilogram, but this is for the passage. So you have 15 passages, and to calculate the power, multiply it by the number of passages, because every passage has 1 kilojoule per kilogram. So the more passage you have, the more power you extract. Okay, multiply 1 kilojoule per kilogram by 15 passages, and then multiply it by the total mass flow rate to get the power. This is the method of calculating the power by the enthalpy difference. I think this method because the total enthalpy at point 1 is not the enthalpy of the one passage. Okay, it's the total enthalpy of the whole turbine at the inlet. So we have 15 passages, and every passage has 100 kilojoule per kilogram. So you have to add all of them and then multiply it by the mass flow rate, and also 0.2 and 0.2s. Okay, gentlemen, we have finished our tutorial. I will leave these papers after in the description to check it out. Okay, I think that it's okay now, and I hope to use this tutorial for your simulations. I hope it works with you well. والسلام عليكم ورحمة الله تعالى وبركاته.